Hi, Ben.
How's it going, John?
You know, I haven't talked to you in so long.
I know it's felt like ages since I was last put in a headlock by you, and
I know. Or are you still in it?
No. I definitely at the end of the last episode, or I guess it's unclear where in the chronology it kind of exists beyond.
Yes.
So imagine like a quantum state where I am perpetually in kind of like joint
right.
lock at all moments, but also
in constant terror, either of it not having happened yet or it currently happening.
Or happening for all eternity, effectively.
Perhaps to help explain, we are doing a bonus episode, which is not an exclusive episode, just bonus. It's just for a happiness.
We following it.
And we're doing it on the 2024 edition, which means that it doesn't fall at any particular time, because as we all know, the year in the editions is only loosely related to the year of when you get to start talking about the edition. So the 2024 edition of Rust officially became supported by Rust 185, which came out in 2025.
In like March or January or some early part of the year. So effectively it was stabilized 2024. And so just barely qualifies to still be called the 2024 edition.
I see no problems.
And we don't disparage, right? Like it's a lot of work to get
No.
So
we are only happy about all the things we got out of it. Now the 2024 edition has a decent amount of stuff in it. I don't know if we were to try to compare size-wise how impactful were the different Rust editions, this one feels like moderately big. Like I think 2018 was very big, right?
It's only been
three
real editions so far. And so it's hard to this is our first time establishing a real, if you imagine a trend line with just 2 points, it doesn't really show anything. With 3, right, we're starting to get to the point. I'd say it's pretty big. I'd say it's fairly impactful.
But it's not like lots of things radically changed. Like I feel like with 2018, we got async await. That was pretty big.
All paths and modules had new stuff in 2018, right?
And we got non-lexical lifetimes in 2018.
So yeah, I'd say there's lots of little things. And so as Rust gets older, we're noticing more of the little hairs kind of in various places and trying to file down the sharp edges, but there probably aren't too many of those large things to file down at this point.
So I think what we'll do is we'll go through all of the things and talk about them in as much time as we think is necessary to convey roughly why and what and the excitement we feel for them.
I'm very excited. Are you excited?
I am so excited.
All right, let's start with the RPIT. What it was RPIT lifetime capture rules. What is RPIT? What are lifetime capture rules, John?
So I think I've had rants about this a couple of times, but RPIT is return position impl trait. So when you have a function and in the return position of that function's signature you have impl trait, then that is return position impl trait. And as we've talked about before, the rules around lifetime capture, for impl trait is a little subtle. So imagine you have a function where the arguments, include references that have lifetimes or types that have lifetimes, and your return value is an impl trait. Then does the type that gets returned, does it capture the lifetimes they came in? Are they constrained by the lifetimes they get in? So the example here being, let's say you take a stir argument, like a reference to a stir, and you return, let's say, an impl future, and that future carries with it that same string reference. Well, that impl future is now constrained by, it's related to that input lifetime of the stir. And the RPIT lifetime capture rules are basically the automated rules that Rust uses for determining when you have an impl trait, which lifetimes from the input get captured. And these rules were fairly subtle until the 2024 edition. And crucially, they vary depending on whether you were using async functions, which desugar to return position impl trait, or you were using return position impl trait in traits, or you were just using it for normal functions that were not in traits. In the 2024 edition, the rules are actually now much simpler. The rules are all in-scope generic parameters, including lifetime parameters, are now captured when you have return position impl trait. So any generic, if it has a lifetime, it will sort of infect the type, the impl trait return type. If you have a lifetime argument, that's going to get captured in the same way. And you can opt out of something being captured using the use syntax. So this is, you have in return position, impl trait, and you write plus use open angle bracket, and then a list of type parameters and lifetime parameters. If you give a use bound, only the things you list are captured and nothing else. And so as a result, the default rule is pretty simple. Everything gets captured, and then you can be more explicit if you wish. Like if you, for example, want to say, the lifetime that is associated with this, stir argument is not captured by the concrete type behind this impl trait, then you can now say so using the use bounds. And like the reason they changed this was partially because, well, the previous one, you had to know lots of different rules. So this was like to make it consistent, but it was also because the workaround people used for the compiler error they got, if they had an impl trait that captured something, then the compiler would say, well, the concrete type here needs to use this lifetime. And then people would add like plus tick A after the impl trait, which is actually incorrect, but that's sort of what it seemed like the compiler was telling you.
Right. So why is it incorrect? That's my question is, so how is plus use tick A like something different from just plus tick A, which has worked forever?
So plus tick A is wrong because it implies that the returned, concrete type outlives the input lifetime. It lives longer than the input lifetime.
Or at least as long as.
At least as long as the input lifetime. The reality is what you're trying to express is that it lives at most as long as.
Oh, wow. Okay.
So it's actually wrong in the other direction. It happens to work because
in the case where it's exactly
as long as it happens to work. But this can get really complicated once you get, things that are, lifetime invariant, for example, then this gets painful real quickly. And so the thing most people do is incorrect, and there is a way to express it correctly using this thing called the captures trick, but it's really subtle and no one does that. And so now having this explicit syntax lets you very easily express what you intended to express, and also makes consistent all the behaviors across all these different places where we have return position impl trait.
So up next we have if let temporary scope. There's actually a few changes here with regard to the same changes. There's if let temporary scope as well as let chains in if and while. Let's start with let chains. And so we talked about this. I'm not going to rehash too much, but in either the past or the previous episode, talking about let chains, where the idea being, hey, I have an if let. I want to be able to use like normal conditions, like having a normal if. You can do if foo ampersand bar. Right, and have like these short-circuiting logical comparisons where it stops at the first one that fails, effectively. The ability to use those in conjunction with let bindings in an if statement. And so this has now been a long requested feature, and it could not happen because of some trickiness with regard to temporary variables and when they get dropped. And the way to finally resolve this was to say, hey, over an addition, the lifetimes of temporaries in these positions have now changed, which is technically a breaking change. It's one of those like really strange things where if you do a cargo fix to upgrade your code to the new edition using this, you might see a lot of really weird stuff where it's now trying to like contortedly guarantee that the drop order is exactly the same as it used to be because you're doing an if let in a certain way. And the lifetime is now shorter.
But what is a temporary?
Right. So, if you might be used to thinking about things in terms of like bindings and Rust. So if I emphasize let x equals 2, right? You don't really, it works in C as well, right? And so like C has automatic memory management. It's just called the automatic storage duration, right? Where it's like, hey, at the end of the scope, just like, I don't care, get rid of quote unquote this int, which doesn't actually do anything, but like, yeah, we can't access it anymore. And so, and in Rust, if you have like let x equals string : new, right? Okay, well, the string itself will get deallocated in the same exact way at the end of this scope. But what if I say, let x equals string : new dot len, right? And so now x is the length of this new string. So x is 0, right? But when does that string : new get dropped? And so often this does not matter, because often structures have no real useful side effects that are not being observed in any useful way. Sometimes it does matter. And so I think mutexes are the biggest example, right? Where like when a mutex gets locked or unlocked is a pretty big deal. Either can cause deadlocks or it never cause anything like a race condition, but it might cause a deadlock if you like drop it in the wrong way or leave it alive for too long, effectively. Or I guess a live lock. Is that what that is?
Yeah.
So,
well, depends on the system.
Sure. But the idea being that sometimes it does matter with the exact sort of, durations, the scopes of a destructor. And so, if this has happened before too, this has happened in the wild where people have like, locked a mutex in the condition of an if, because it has this variable you want to check and it's guarded by a mutex. So let me lock this and get the guard out. Now the guard's doing this thing and I reference it. And so if, some behavior changes, with regard to like when Rust drops that value, it could change your program. Either it stops compiling, which is the best case scenario, or you get a deadlock of some kind, which is, the worst. And so, now also we talked too about like, where intuitively we look at code and we think, hey, like when will this value be dropped? And so again, let's talk about like let x equals string new : dot len. Or like, when do you think that like that string, which is never named, right, never bound to any variable, when's it get dropped? And so conceptually, it's at the end of the statement, right? When you get the semicolon at the end there. And I think if you can do this yourself, I'm pretty sure, right? Temporaries are pretty subtle and pretty obscure. And so if I'm wrong here, I'm sorry. But I think generally it's at the end of the statement for things that never actually get bound. But there are some times when they get promoted, but sometimes when they're not. And so if you've used Rust before, you've probably noticed, hey, sometimes you're doing a thing and then you'll get an error message that says, hey, like break this out into its own binding because this doesn't live long enough, right? You're taking a reference to something which is now going away. And so it says, hey, like bind this thing to a reference above this statement. And then that creates no longer a temporary, quote unquote. It's a named variable, which will be dropped at the end of its own block, like normal. And then it makes it easier for the compiler to say, hey, like now I understand you meant to, the lifetimes of this thing, etc.
Yeah, it's like make it explicit that this thing actually lives to the end of the scope rather than to the end of the state.
Yes. And so kind of, letting you control when a thing is destroyed, including things that never get named and couldn't otherwise be referred to, right? And so, think about, a match though. And so if I have match foo, and then I have some braces and I have some stuff inside, when does foo, right? Let's say foo is a temporary, because I could be saying match string new, match vec new. When does foo get dropped, right? Well, you say, looking at it how naturally, you think, okay, well, match foo, and then some stuff happens probably at the end of the next block, right? That's natural. And that is how Rust works, right? Think about what if foo. And if you say if : string new dot len equals 0 or whatever, right? When does that string get dropped? Well, at the end of the next brace, but wait, ifs allow trailing else clauses, which might have their own else if branches, would have their own else's in there somewhere, right? And so again, the natural way of thinking about this is that, okay, the temporary in the condition of the if is dropped, before the else happens, right? Which is very natural and useful. The thing is, for if let specifically, often if you're writing a language, it's nice to do what's called a desugaring, where you don't need to like write code to handle multiple separate things entirely from scratch, like if and match, right? You can say, oh, like if can be compiled to a match. I can transform this if into a match and then just write the code for the match once and generate code for a match. And you see this with like, imagine, the loop keyword. Rust has while loops and for loops, but a for loop can be desugared into a while loop and a while loop can be desugared into a for loop. So really you just need to write like, code fundamentally that does looping at the end of the day. So it makes things much easier, fewer things to, handle in your compiler. It's a great strategy, used all over the place. The thing is, and so, when if lets were written, they were desugared to a match, because conceptually they are just, hey, I'm going to, match on this thing and then shove the condition inside of the successful arm and ignore the rest, right? But that means that the temporary inside of this lives to the end of the match, unlike an if. And so it wasn't really appreciated for a long time, because often you're not thinking about these kinds of things. And so, this change had been made. And so to bring if let in line with if. And so now it would be weird if, temporaries in an if let were had a longer lifetime than those in an if. And this also just makes things consistent and easier to use. And so now you've learned way too much, and yet you barely scratch the surface of what temporaries do and how they work. There's a whole, Mara Boss has a really great blog post. I think her original post on Superlet, talks about like, temporaries in Rust or any language really are strange. Yeah, they're strange in all languages. Rust just actually makes you care about them because suddenly lifetimes are next thing. Well, I guess like you care about him in C and C++ because he's also C++ is RAI and, also has lifetimes. So.
There's another part here to the 2024 edition, which is that tail also related to temporaries, which is tail expression. So if, in Rust, you don't need to write return if you want to return whatever the value of the last line or last expression is. You can just leave that expression there and it's sort of an implicit return. So that's called a tail expression. And temporaries that are generated in the tail expression in the 2024 edition now also can have different drop rules. So in particular, they might get dropped before local variables are dropped rather than after them, depending on the phase of the moon. Now, I don't know exactly why they needed to loosen up the rules here for tail expressions. It might have to do with like eventually supporting tail recursion, maybe. I'm not sure.
I don't think that has to do with this. I think it really was just there are certain patterns. Right. So temporaries are like interesting because you want things to work. Imagine you could never write let x equals string : new.len. It made you write let a equals string new, let b a.len, right? Which would be like correct. But people often get mad when you like can't chain things, right? Imagine never being able to chain anything. And so, people want temporaries to exist, like sort of just like intuitively. But they also want whatever they want to do what they want to do. And so Rust often tries to walk this tightrope of like being precise and like, simple while also letting people, just not have too much ceremony. And so this kind of like originally, right, we had the borrow checker was a very simple sort of like simple quote unquote, right, lexical scheme where it was like, hey, like a borrow is just as long as you're like literally into the next brace, right? Which was, more restrictive than lots of folks wanted it to be. And so nowadays we do not have this. We have non-lexical lifetimes, NLL. Well, and so, the way we describe it is, there's a dichotomy between, do what I say and, do what I mean.
Or do what I want.
Do what I want. It's like, please just like do the right thing here.
Yeah.
Which often the compiler could do, but at the expense of adding more rules and trying to figure out, hey, like what is actually happening here? And so it's a very hard balance to hit. And so in this case, I really think it was just people wanted to write code. There's an example here, right? Where it's like you make a ref cell, you borrow it and then get the length of the thing inside the ref cell. But that doesn't compile because, the intermediate variable gets dropped before you actually return. And so it requires you, like we talked about, to like create another binding to like, again, control when this goes out of scope. And so people want to be able to chain things, right? People want to be able to write these chained expressions, and without understanding or having good intuitive temporary, support, this isn't possible all the time. So, were you talking about before with the old, like the recursion of the tail recursion, right? I think it's a totally different, separate sort of thing.
Okay. This next one is also like a sort of compiler tightrope of match ergonomics. So, the RFC 2005, introduced this notion of match ergonomics, which is, imagine that you do let some x equals and then, some option value. Rust has to now, or let's rewind to before RFC 2005. What this would mean is that X would move out of the option. So if you used if let or match to match on an option and you wrote some X, then the option would be consumed, would be moved by the pattern match, and then X would now be an owned value that is the thing inside the sum. And I think this confused a lot of people because they were like, well, I just want a reference to it. And then the thing you had to write was like, if let sum open paren ref x end paren equals, and then the name of the option. And then Rust would understand that you're not consuming the option. You're instead just taking a reference out of the option. And people are like, well, can I just not write ref? And part of the inspiration here, I think, came from closures, where very often closures can be sort of magical in this way, where they kind of understand which things you want to take by reference and which things you want to move. Sometimes you need to use the move keyword, but you don't need to like write ref or ref mute, like for individual things that you capture. People are like, can if let just do the same thing? And so RFC 2005 introduced this notion of match ergonomics, where Rust would now look at the type of the scrutiny and figure out what kind of matching you probably meant to do with the sum x pattern. In particular, what it would do is if the type of the scrutiny is a reference, then the pattern is assumed to also want to try to match a reference, because it doesn't make any sense any other way, right? If the value of the scrutiny is like a reference to an option string, then trying to match some x on it will never work because you're not allowed to move out of the option. And so like, well, clearly here, the user must have meant that this should be a match by reference. And so why don't we just make the language do that for them? And hence match ergonomics. Now, the thing where this got a little weird is what happens if people start to mix and match these. So what if it happens if you have a match ergonomics thing like this, where the compiler infers that you wanted to match by reference instead of by move, but then inside of the pattern, you write ref mute. So now the compiler is like inferred that you're supposed to use ref, but then you're also trying to use ref mute, and the compiler gets, let's call it, upset. And prior to the 2024 edition, this would like kind of be, allowed, I believe.
Yes.
Like you would be able to write, for example, so let's say you have a 2-element array with, the values of that array being 2 empty tuples, and you have a reference to that array. So you have a reference to a 2-element array where the value type is tuples. If you try to write let open square bracket x comma mute y close square bracket and match it against that reference to a 2-element array, the pattern matches, but the question now is, what do x and y get mapped to? Well, x is going to be mapped to a reference. Y, it's going to try to map you to a mutable reference, but it can't because it's inside of a shared reference. And so this is just weird. It's like not what the user probably intended. And then we'll get an error saying something like, cannot borrow mutably through a shared reference. Instead, now in the 2024 edition, you're not allowed to mix and match these. So if you want to use explicit matching on ref and ref mute, then you have to use explicit pattern. You cannot use this match ergonomic style. So in this case of the reference to the 2-element array, you would need to say let ampersand square bracket ref x comma mute y close square bracket. So you would exhaustively have to match on the pattern. You don't get to have the compiler infer for some of them how it should match, and for other you be explicit. You have to fully match or use the ergonomics.
Yeah, I think it's a great example of what I was talking about before with the idea of, okay, we start with having just kind of like simple rules, and then people get annoyed at the simple rules because they want to do kind of like, just why should I need to bother with this? So this, originally, Rust 2015 started with kind of like, there's no ergonomics, quote unquote. They're just like, you need to bind every pattern with a ref everywhere in there was ever kind of like nested at all. And then 2018 changed this, and now we're kind of like tightening it up a little bit more in response to kind of like understanding how people actually use it in practice. Unsafe extern blocks. And so this is about, extern blocks. And so if you have if you want to write a single function, or sorry, you've heard of like extern functions. I can write extern C, fn, whatever, and now that function now has an ABI that is compatible with being called via the C compatible ABI, and so you can expose it as though it were a C function and call it, and it just works. If you want to declare functions that are defined elsewhere and then call them, assuming that they have been defined, you can use extern blocks. Right? And so in the same way, you can have this kind of extern C block and then define a bunch of functions inside of it and then say, hey, like, assume that all of these exist, right? There's no bodies in there. They're just signatures, and names, right?
And the linker will...
Yes, the linker knows what to do at that point. Like, so there's going to be somewhere in the object file a function called foo. So if you write unsafe extern C, you can brace, and then down here, foo. And that just defines a symbol, pre-declares it effectively, so that Rust itself knows knows stuff about types actually call the function. So some changes to the extern blocks are that this idea that the point of the unsafe keyword in Rust is to, I don't want to say assign blame, right, but is to be precise about whose job it is to uphold certain invariants, or kind of like whenever something goes wrong, where is the code wrong at?
And even just to highlight that there are things that could go wrong.
Yes. And so naturally, when you call any function, like as though it were a C function or like from C, it's often going to involve dereferencing raw pointers or crossing an FFI boundary. All the things are inherently unsafe and require the unsafe keyword. But even defining the function is now considered unsafe in the new edition, with the idea being that, hey, if I'm just the one calling a function, I didn't get to declare the type of the function. And so if the declaration itself is wrong, then the blame, quote unquote, is with the person who defined the function. And so now extern blocks can be marked unsafe. It's not required, I don't think, right? It's just like...
No, I think it's required. They must be unsafe now.
Oh, I see. The ability in all editions to mark them extern unsafe, but it might be that in the new edition it's required. Yes. And then within the extern block, whereas before, all the functions would be unsafe, or I'm not sure if it was implied unsafe, or actually you wrote unsafe on the extern.
It was implied.
Right. And so it's still implied unsafe. And so kind of like any function you declare in here must use an unsafe block to call. But now you can use the safe keyword, right? Get the contextual, just like write safe in front. And now it's possible to declare a C function that is in fact safe to call, which actually is possible in theory, right? It's again up to you, because you are the one declaring it. If you erroneously mark a function as safe, that's obviously undefined behavior, because for example, let's say a C function that just takes like, a U8 or something, and then does, adds 2 to it and returns it, right? It's trivial to see that there's not actually any way that C function itself could be undefined behavior. I mean, I'm hoping.
Yeah.
in a way, surprises us, but
in a way, what they're trying to do, right, is to separate the unsafety of getting the signature right from the unsafety of whatever the function might do when you call it.
Mm-hmm. And so with this hypothetical add 2 to a U8 function, I guess it could overflow undefined behavior. But anyway, we'll ignore that. If, say, the definition of the function changes and now you're doing a null pointing to reference or whatever in there for no good reason, right? Like Rust can't check that, because again, it is in C, and we are assuming that like your assertion here, this safe keyword where you have put it in front of the function, is an assertion. It is actually a safety invariant where you're saying, hey, I assert it is safe to call this function, because if I hadn't written this, by default, it would have been considered unsafe. And so I'm allowing other people in the program to omit the unsafe keyword, because I'm the one here taking responsibility where if something goes wrong, I'm to blame, where I am the unsafe extern block here. So what's next? Unsafe attributes. So yes, another interesting kind of like consideration, right? If you've like used unsafe in Rust before, read the Nomicon, you've kind of understood that there aren't a huge number of things that unsafe lets you do. Again, you can call unsafe functions, lots of those, right? But it's calling an unsafe function, referencing a raw pointer, asking a static mute,
and transmute.
Well, that's still a function. That's just a function.
That's true.
Right. And so, the idea of, well, what is unsafe? What can possibly lead to memory unsafety? It's generally a pretty constrained set. But something that we realized, pretty early on and didn't really know how to handle it was, the idea of the no mangle attribute, or even just in general, attributes in general, can attributes cause unsafety? And the answer is yes, because attributes can influence code gen and do things that are visible to the outside in ways that other parts of your process, your pipeline, your tool chain might then assume things that are required to uphold safety. And in particular, in C, if you have you can, if you write in C, like int foo, I define a function foo and do whatever, right? If I define two functions in the same unit, or even if I try to link multiple object files together with the same symbols, because C doesn't do mangling of symbols, what happens? That's kind of like, it's whatever, man. And generally, these days, I think like some linkers will try to error out or warn you or let you say, hey, if this does happen, please give me an error. But Rust can't guarantee that behavior, and there are linkers out there that don't do this. And so, what if I use the no mangle keyword and then like find like 6 different symbols in the same unit that all have the exact same symbol at the end of the day? Like, what should happen, right? If I try to like, if I have a foo in this crate and a foo in this crate and link them together, now what happens?
Yeah, and they both have no mangle on them.
And they both have no mangle on them. And so the idea being that Rust cannot guarantee that actually anything at all happens, right? Because they could have different signatures entirely. They could have totally different, ABIs. And so you could be trying to call a function with an int, and actually it takes, 6 strings or whatever, and who knows what's happening. And so actually the no mangle function is demonstrably unsafe in these conditions. And also there's equivalent to no mangle is this export name thing where you kind of just say, hey, like this should have this symbol name. And so the idea of unsafe attributes is new to this edition, where the idea being now, whereas previously it was just, hashtag bracket no mangle, now it's hashtag bracket unsafe no mangle. And that's pretty much it. And I think there's just export name, link section, and no mangle right now. And who knows in the future if that will increase. And we also have unsafe op in unsafe fn. I think this is a really cool thing too. So the idea of an unsafe fn in Rust, because it kind of like represents the maturation of our understanding and communication about what unsafety is. And the idea being that the unsafe keyword can be applied to a function, but also to a block, right? You have inside of any function, you can write unsafe whatever and then do something gross, or you can write an unsafe function. But these actually mean opposite things. And so an unsafe function means, hey, to call me, you must uphold something. But inside a safe function, an unsafe block means, hey, I'm going to uphold something. Trust me, bro. Okay. And so it's about like, one of them creates an obligation and one discharges an obligation. And so in theory, I think it would be nice if we had picked separate keywords. I think promise for like the unsafe block, like I promise that I will do this. Like, so you have an unsafe function and then you would have like a promise inside of it. That's just my proposal, my pie in the sky idea. Right. But the idea being that originally, writing an unsafe function just implied that the entire body of the function was an unsafe block. And so you could do any unsafe thing you wanted inside the body of the function, which is just wrong, because the point being that, and now that we understand more about like, we have better tools for articulating what this actually means, is that there's no reason that the body of an unsafe function should be entirely unsafe. Not only is it kind of like imprecise about, where the actual operations that are unsafe are occurring, right? There's a reason surely that you made it unsafe. But also they represent different things, right? They're really different keywords, just happen to be the same, keyword in the day.
It's also kind of a foot gun, right? Of now, because the entire function body is sort of implied to be unsafe, you could also easily end up calling additional unsafe functions in there without even realizing they're unsafe. Yes. Because you're just automatically allowed to call anything unsafe inside of an unsafe FN.
So in the new edition, the body of an unsafe function is no longer an implicitly unsafe context. And so I think this is a great change, really makes it more precise about what unsafety means and separates out these two notions of, creating obligations and discharging obligations.
It's also worth noting that this is a lint that is currently set to warn. And I think they're hoping to eventually set it to deny, maybe. Mm-hmm. But it does also mean that if you have a, particular module, for example, where you have lots of functions where you really want all of them to they're all just unsafe to call and unsafe bodies, then you can allow the lint for that file. That's totally fine.
Mm-hmm. Up next, we have disallow references to static mute. And so this is a pretty pernicious one. It's kind of hard to express. Like I can't express it, but it's not obvious initially, right? And so Rust has statics and Rust has static mutes. And it's always been unsafe to access like dereference or whatever, right? A static mute variable, like mutate it or even read from it. And why is that, right? And so one of the interesting distinctions between Rust and C is that by default, all Rust code is thread safe. It's all reentrant. If I have a safe Rust program, then it is, in C terms, reentrant, where I can call it from multiple threads, multiple processes. It just works. But static mutes are different. And so they've always required the unsafe block to access, but this is about taking references to them. And so one of the invariants of a reference, like a shared reference, right? Or even, either shared or mutable, is that you can't mutate through it, right? And you can't, have a mutable reference to it at the same time. And the thing is, because static mutes are sort of like global to the global scope, if you had multiple threads accessing, calling this, so you have one function that takes a reference to a static mute and then call that function multiple threads, you will have multiple threads that could be mutating the same value in an unsynchronized way, which is just unsafe, right? But the thing is, like, what's the big deal, right? We already have to use the unsafe keyword for this. But the thing is that if this is actually in Rust, there's things about, like, I forget what the exact, the terminology is. It's like, library UB versus like immediate UB versus something else, where it's like some things are only UB when like you do something. And so like for example, having a raw pointer that's just like bogus, if I just like make a null pointer, that's fine. If I just like take the value 6 and assign to cast a raw pointer, it's not a big deal. It's only a big deal when I actually use the pointer, right? But for references, even having an illegal reference in this way is immediate undefined behavior. And so it is basically impossible to guarantee that any reference to a static mute, is kosher, right? Because how do you guarantee that no one's ever going to call this code in any sort of parallel or like reentrant context, right? And so it's just nonsense, as far as Rust is concerned. And like in theory, you could do it if you like had total control of the binary and all the dependencies, right? And so it's not like you're totally wrong here, but the other observation is that you don't even need this, right? And so you can do intermutability. And so like an unsafe cell equivalent. Right now, unsafe cell is not static. And so you can't store it directly. You can't actually use unsafe cell in a static variable, but it's not hard to make an equivalent unsafe cell that is like a racy unsafe cell, a static unsafe cell, and just put that in a static, right? And that kind of, then at that point, it's up to you to like any other unsafe cell. There's an unsafe operation to actually access the contents, and then you can do whatever you want with regard to synchronization, etc. And so the observation that static mute is just not needed. You can just use a static with internal mutability.
Yeah, and the addition guide also has some outlines of alternatives, where the top alternative is just don't use globals in the first place, like use statics. And then it's obviously like you prefer to instead use a non-mute static. And then use atomics or mutexes, like something that gives interior mutability, maybe use once lock or lazy lock, whatever it might be. But they do say, or you can have a static mute, but if you're going to have a static mute, you better only be using raw pointers with it. And this includes using, like, when you want to get the pointer out of one, you can't use, ampersand or ampersand of the static as star const. That will also not work. You have to use the whole like raw pointer, raw references, thing that got introduced relatively recently, by using the raw borrow operator. So you have to write ampersand raw space mute space name of the static to directly get a mutable pointer rather than ever going through a reference.
All right. So I think the lesson here too is that if you have a static mute in your code base, don't use it.
Yes.
Change it to anything else. There's better patterns.
Yes. I think that's right. The next one here is the never type fallback change, which I know we talked briefly about in 180, which introduced this lint, although that lint was originally allowed, and then it got turned into warn, and now I think it's denied by default in the 2024 edition. The change here is a little bit subtle, but Rust has this thing called the never type, also written as just exclamation mark, which indicates that a type has no values. Like, it is impossible to construct a value of this type. So for example, if you have a function that returns the never type, one way to satisfy that is that the function itself is an infinite loop. And so Rust can guarantee that this function will never return, and it's sort of expressed in the return type of the function that the return type will never be produced. This never type is useful in a bunch of different ways, but primarily because it lets you assign in the type system to say that something will not return. And then you can build abstractions on top of that. What gets weird is, imagine you have some code where in one branch you are calling a function that diverges in the sense, so that it returns the never type, and in the other branch it returns like U8. Then Rust needs to check that both arms of the if have the same type. This is just normal part of type checking. But that means that the never type must be considered okay to be sort of interchanged with U8. But it must also be interchanged with any other type. So the never type has to be allowed to be coerced into any type. It needs to be unifiable with any type. And this is normally okay, but where it can get really subtle is interactions with unsafe code, because the never type in older editions used to fall back to unit, to the empty tuple type. And this could then affect inference, where you could write a Rust program where a value got sort of inferred to have a type of unit because of the never type. And if that value then flowed into unsafe code, the unsafe code would now infer that that value is of type unit. And then you might make assumptions based on that being the case. Now, in the 2024 edition, they want to make it so that the never type does not fall back to unit anymore, because unit and the never type are not the same. So if inference does not have another sort of truth value, like let's say you have an if with two branches where both of them return the never type, then in older editions, that whole if expression would be understood to have the unit type as its expression type. Now they want to change that to have the never type be the expression type. It doesn't fall back to tuples anymore. It just stays never. But that would mean that now unsafe code that might have been written assuming that a given expression had the unit tuple type now might be wrong, because it now gets a value of a different expression. And so this lint, the never type fallback flowing into unsafe lint, which is a mouthful, is now denied by default, which it basically checks that you don't have any expression that evaluates to the never type, used to be coercible into the unit type, flows into unsafe. That sort of pattern is now disallowed because the fallback type is going to be changed. And so as a result, they don't want to take the chance that unsafe code now has some of its requirements or its implicit assumptions be violated. The next change here is about macro fragment specifiers. So, in the 2024 edition, the macro fragment specifier expr now also matches, const and underscore expressions. Now, fragment specifiers are when you write something like macro rules, then for each argument to a declarative macro like that, where you write, for example, $E:, you then have to write a fragment specifier that says, what is the type of this fragment? So for example, you can write $E:, EXPR to say this argument is any valid Rust expression. You could also write $T:, type to say this must match a type. Now, the meaning of expr has changed in 2024 because expressions now include things like const expressions where they did not previously. And you might think, well, why don't they just say that expr now includes more things? And the answer to this is because they don't want to break backwards compatibility. They want to make it so that if you have macros inherently cross crate boundaries, right? So if I write a macro in a crate that uses the 2021 edition, and I write expr in there, then if I call that macro from something in the 2024 edition, it should still match only the things that code expected it to match in 2021. And so for this sort of interoperability story to work, there has to be a way for us to represent the fact that in the macro definition here, its meaning of expr is not the meaning of expr in the 2024 edition. And so as a result, we've ended up now with two different fragment specifier for expressions. There's expr and expr underscore 2021. And expr underscore 2021 only matches the things that would have been matched by expr in 2021. And so now the sort of addition mechanism takes care of figuring out which of these to use. So in 2024, in macro rules in 2024 crates, when they write the expr fragment specifier, they will match const and underscore. But if you write it in a 2021 expression crate, it will be understood to mean the expr 2021 fragment identifier type and will only match those things.
Yeah, I think this is a kind of a newish policy. Back in 2021 edition, we definitely made some changes. I wrote an RFC for raw strings, or arbitrary identifiers, arbitrary prefixes for strings, for things like f strings, etc. And so one of the blockers for that had to be an addition was because what if macros are looking at a literal and they see f and then followed by a string literal, they might parse it differently based on the thing. Right. And so we just we'll just be careful and lint and do a check and then do a crater run and see if anything breaks. Nothing actually broke. And so, but I think this is kind of a new policy of trying to be more conservative about hey, we'll just have a different parser for it.
Yeah. I think it also comes down to how likely is it to introduce breakage, right? So in the 2021 edition, there was something similar around OR patterns where we introduced the ability to say in 2021 edition, you could now write some open parentheses X pipe Y end parentheses to say, I want to match some and X or Y inside of there. Whereas before that, you could only have the OR in patterns at the top level. And so that also then changed the way macros might parse a thing called a pattern. And so in the 2021 edition, they had :pat for matching patterns, but there's also :pat underscore param, which matches the newer type patterns as well. So there's sort of been a recognition that we need to be able to talk about the kinds of patterns or syntax that was allowed in different editions, even back then, as in, 4 years ago. We also have a bunch of more reserved keywords in the 2024 edition. This happens every edition. We get more reserved keywords. Most of them, and some reserved syntax as well. Most of them are really just to kind of set ourselves up for the next edition where we might want that keyword to mean something. So we reserve it in one edition, so that programs stop using them, so that in the next edition we can introduce new well-defined behavior for them. And you often, if you already knew what the implementation was going to be, you wouldn't need to do a cycle of reservations, but this is more of we think that in the next 4 years, we might get an implementation of something that uses this keyword. So we're going to reserve it now to sort of give people more time to adapt to it. And in particular, in the 2024 edition, the gen keyword is now reserved. The intent here is that this is going to be used for generators, which is sort of think of something like the equivalent of async, but for iterators, right? Where I want to have a generator, which is a function that when you call, it actually returns instead of returning a future, which is the case for async, it returns an iterator. And it gets an additional keyword in there, yield, which is already a reserved keyword that lets you say this function will actually sort of return, quote unquote, multiple times. And each time it returns, it's really just a value that gets yielded from the iterator that the function actually returned from the caller's perspective. But the migration here is really just there's no implementation of generators. It's just reserving the keyword.
So changes to the prelude. This is now standard library changes. And so the idea is in standard library, there is a thing called the prelude. So if you've ever written Rust code and wondered why you don't need to say import option or some or none or vec, because there is this thing called the prelude, which is implicitly imported into all Rust code by default. You can turn it off if you want to, as a no prelude attribute. But it's kind of like just generally useful things that you probably want to be in scope. For general, it's great for like writing, like print line, for example, is in the prelude effectively, right? It's a macro, whatever. We'll talk about it later. But the point is that we've added new things to the prelude, one of the being the future and into future traits. So that would, if you ever import future or into future, you now no longer need to because they are now in the prelude. So, I think we added a few things in the previous edition as well. So, you're talking about IntoIterator for box T?
Yeah, so the IntoIterator trait, or IntoIterator trait, is the thing that allows you to loop over things. Like when you write for x in foo, implicitly what happens is there's a compiler-injected call to .IntoIterator on foo that uses the IntoIterator trait. That's how it takes the thing that comes out or after in the for loop into something that it can actually iterate over. The IntoIterator trait has existed for ages, but imagine that you have a box slice of T, but where that slice is owned, it's not borrowed. So it's sort of, to read the full syntax, is a box, open angle bracket, open square bracket, T, close square bracket, close angle bracket. The IntoIterator for that type really should yield owned elements, because you have a box that owns a list of values. And so IntoIterator, the point of the into, as opposed to just a normal iterator, is that you can turn it into a thing that yields all of its elements. Just like if you call IntoIterator on a vec T, the type of the iterator is T, not reference to T. However, in the previous editions, what would happen is that IntoIterator was not implemented on box of slice of T. Instead, what would happen is IntoIterator was implemented on references to slices of T, and box derefs to that. So when the compiler did a .IntoIter on your box of slice of T, you would actually get borrowed T's out, because you end up using the IntoIterator implementation of the slice reference over T's. This is not what you want to happen. And so in the 2024 edition, this behavior has actually been changed. So now it will use the IntoIterator implementation by the box itself. But obviously, this has to be an addition boundary change, because that's not what old code would expect. It's been written to assume that what it gets back are the references. So we can't just change the types here. And there was actually a decent amount of mechanism that had to be figured out here for how can we make it so that the compiler knows to use a different implementation in the older editions than the new one. Like, how does it know to, like, use the deref even though there is an implementation on the type itself?
Sure. And so this problem was solved in the previous edition, where an analogous thing happened where we wanted to implement the iterator for arrays. And previously, our iterator was not on, like, as in a fixed size array. It was only on slices, and because of the auto reference behavior, same as here, or similar to here, if you call .iter, it would give you references, to, the thing, as opposed to actually, giving you the owned behavior. And so, yes. And so, this was solved previously, but it wasn't kind of extended to boxed, of owned values, of owned, it's hard to say slices. Normally when you say slice, we just mean, like, behind a reference. You can use, like, a dynamically sized slice behind any, sort of, like, quote unquote smart pointer like this. But yes. And so, we really, I'm pretty sure, I'm not involved with this, but I'm pretty sure it's just using the same machinery as previously to kind of say, hey, like, which edition are we in? If I see this, it acknowledges that it exists, but it ignores it in old editions. That's what I assume it does.
Yeah. It's also interesting that the IntoIterator for box slice of T was added in Rust 180. And so it was only after that, I think, that they realized, but it doesn't get used.
Mm-hmm.
Even though we've added it, like, you can't have it be used.
You could always use it in the old edition by using the fully desugared, fully, explicit, method called
like a universal function call.
Yeah, whatever you want to call it. So you would be like, angle bracket into it or box whatever as IntoIterator angle bracket : iter or whatever. So,
and it's worth interesting that, it's worth noting that actually there's sort of a slight simplification here. When you, write 4x in a box slice, that actually works fine on all the editions because the 4 desugaring doesn't actually use automatic dereferencing. Like it won't deref the box and then call IntoIterator.
Yeah.
So it's only if you use the explicit calling syntax, you write like 4x in box slice dot IntoIterator. Like if you wrote that yourself, that's the thing that doesn't make use of this new trait implementation.
Because the desugaring doesn't actually use methods, it's called. It does it does effectively the fully explicit, method call syntax, the UFCS, whatever you want to call it. Up next, we have some newly unsafe functions, some functions that were safe in older editions and became unsafe in this edition. We have, env setvar, env remove var, and then OS Unix process command X before exec. And so setvar and remove var have kind of a long saga. We can link to it. The idea being that these are kind of like wrappers over kind of the idea you have environment variables. I want to mutate them. And so the thing is that this is not thread safe on Unix, kind of like by definition, despite some attempts to do various hacks over the years, with the idea being that it's just a raw pointer. And so no matter what you want to do, there's going to be there's nowhere to hide any kind of weird behavior in here. And so, even though Rust for years has implicitly, if you used locking, and so if you had multiple processes or multiple threads, I should say, multiple threads trying to both set and or read the value of this environment variable, they would use locking internally, but as long as you use the Rust library versions, because you could still be calling, any of the C implementations, which weren't using, synchronization, or at least
they weren't aware
of the Rust side synchronization, and so they can be doing whatever they want, and that's totally standards compliant. And so after years and years of trying to figure out what is the right behavior, it all kind of sucks. Everything here is terrible. I guess we just gotta mark them as unsafe. So that's kind of just the solution they've wrapped upon was kind of hey, based on our policy, this is unsafe to use, and the safety contract is you must guarantee that nowhere else in your process space is there anyone else trying to call these variables.
Yep.
They're trying to call these functions or
trying to
modify the underlying environment variable.
Yep. I think it's not even just the same variable. I think it's environment variables at all.
Because they're all behind the same.
Yeah, I think
you have torrent rights.
I could be wrong here, but I think it's the case that you actually have to guarantee that no one is modifying environment variables at all. Or conversely, if you want to modify them, you have to guarantee that no one else is reading them right now.
Mm-hmm. Yeah, so I'm sure there's workarounds where you could in your main function just take a copy of the entire environment and put it into your own static somewhere, and then use some kind of synchronization to guard it yourself and guarantee that no rogue C code could mutate out from under you. And there's also the before exec method has also become unsafe. I learned just now because it's an old deprecated method that was deprecated in 1.37. So the second release of Rustacean Station deprecated this. And so, I'm not even telling you what it does to ignore it. It's deprecated. I don't care. Now it's also unsafe.
Next, we can move on to cargo. So there were some changes to cargo in the 2024 edition as well. One of them is that the 2024 edition introduced now implies using resolver version 3 in cargo. So you could set this in your cargo toml even for earlier editions, but in 2024, resolver equals 3 is the default, or the implied default. And the big change to the third resolver of cargo is that it is Rust version aware. So it's aware of the Rust version field in your cargo toml, and it will try to resolve dependency versions such that it picks versions that are compatible with your Rust version. And And it's important to note that it picks versions that are compatible with the Rust version specified in the cargo toml, not necessarily the Rust version you're running. So if you are running Rust, 185, but your Rust version field says Rust 175, then cargo, when it resolves your dependencies, will only update dependencies to versions that are compatible with Rust 175. And so as a result, if you run like cargo update, for example, you would not actually end up with the latest versions of your dependencies. You would end up with the latest version of the dependencies that are compatible with 175. Cargo will print this. So if you run cargo update, at the end, it'll say a warning like, some dependencies were not updated to their latest version, pass -- verbose to see which and why. And the thinking here is that should make it easier to, if you're using older Rust versions, make sure that you don't get broken by people releasing new versions of their crates that rely on new Rust features and you picking them up and now you can't build them. But also for library authors that want to preserve support for older Rust versions, that when they run cargo update, they know that their lock file will still end up with versions in there that are compatible with their minimum supported Rust version. Now, it is also worth pointing out here that when you use this feature, you will end up having sort of outdated dependencies. And so you should probably make sure you check the output here of cargo update and cargo -- verbose to see when you might want to change your minimum supported Rust version so that you get newer versions of your dependencies. Also worth noting that the resolver is a global setting. So if you have a Rust workspace, the resolver gets set in the workspace root. So you can't say this crate in my workspace has this resolver and this crate in my workspace have a different one. You can also change the resolver behavior here. So there's a field, in your cargo config, you can set, resolver.incompatible -rust -version, which defaults to the value fallback, which has the behavior just described. You can change that value to use, other values instead if you don't want this particular, configurations. For example, you can set it so that instead of going to the oldest version that's compatible with your Rust version, you can set it, for example, to simply allow any update, even if it's incompatible. In terms of trying to determine whether a dependency is compatible, or not, it just uses their Rust version field in their cargo toml. So if you have a dependency that doesn't set Rust version in its cargo toml, then it will just get updated to the latest version, and if it breaks, then cargo has no way to know. Also worth noting that if you don't set Rust version in your cargo toml, then I believe this will have no effect. Rust will just update to whatever the latest version is. There's also a smaller change here to cargo where for cargo configuration files, be it cargo toml or your .cargo config, there are a couple of field names that you used to be able to use one of multiple names. So for example, default features, you could write as default _features as well if you wanted to. I don't know what crazy person does this, but that is no longer the case in the 2024 edition. You now must use the sort of standard way to express each field. So it must be default -features. It must be dev -dependencies. You can't use underscores. Same thing with, it used to be that you could use open square bracket project close square bracket as a replacement for square bracket package square bracket. That has also been removed. So now there's sort of a canonical way that all of these things need to be expressed. There's also been a change here. It's not really a change. It's more like a yell at you if you would have hit a foot gun around the use of default features in workspaces where you use inherited dependencies. So imagine you have a cargo workspace, and in that cargo workspace, you have a dependency on, the regex crate. And then you have a crate inside of that workspace that takes a dependency on the regex crate and uses workspace equals true. So it wants to inherit that dependency from the workspace dependencies. If you try to use default features equals false, in that package's dependencies, that is now a build time error for cargo. And the rationale is, well, you're inheriting the dependency from the workspace. The workspace does not have default features equals false. And so therefore you're inheriting all the default features. So when you try to set default features equals false, it actually has no effect because cargo features are additive. So cargo sort of takes the union of all features that are enabled anywhere in the crate graph. And so the union of having the default features from the workspace and turning them off in your particular crate is to have all of them on. And so this configuration just makes no sense, but when people read it, they will think it means you get no default features, which is not what it means. So now that's just a hard error. If you want this behavior, you instead need to set default features equals false in the workspace dependency. And then you can inherit it and set default features in a particular crate as well. And then I think this brings us to sort of towards the end here. We're now talking about Rustdoc, which has seen some 2024 edition changes as well. One of them I think we've talked about a couple of times on the main feed of the podcast, where doctests will now be compiled as a single binary that holds all of your doctests rather than one binary per doctest, which used to be the case for a very long time. This change significantly speeds up the builds of doctests, although it does mean that they have less isolation from each other because they had all compiled into one binary.
Sure, and there is some, I think, other heuristics or ways to control when a doctest is still compiled in standalone mode. I think there's this standalone crate attribute. Is this an attribute or?
Yep. It's a thing you can put after the triple backticks that open a doctest.
I see.
You could put standalone crate to say this must be in its own crate, in its own binary. Then there are also some other things that are implied. Like, for example, if you use the compile fail tag, then it has to be compiled in its own crate because it's not going to compile. So you can't use that to build a binary. And there are a couple of other things around, crate-wide attributes and like, there are a couple of other things like if the doctest sets the global allocator, that would also trigger this because it cannot be shared with other doctests. But in general, for like most doctests, it would be fine for them to be compiled together. And then this makes the build a lot faster. There's also an interesting change for Rustdoc around nested includes. So in Rustdoc, you can, or let's say you write something like, in your crate documentation, you write square bracket exclamation mark. So crate level docs, open square bracket doc equals, which is a way for you to write the doc string you want to be put there as a doc string, but you write it as an attribute, as a Rust attribute instead of as a comment. And the reason you would do this is you can then invoke things like macros. So you can say, square bracket doc equals include stir exclamation mark and then a path. And now that whole path gets included by the compiler and placed as the value of this attribute. And this attribute is a doc attribute, which means it gets turned into a doc comment. And so you can use this, for example, to take your readme.md and turn it into a giant doc comment automatically in your crate. Very handy for this. Now, where this gets interesting is imagine that you include stir a markdown file that itself includes things that will become doc tests. And now imagine that one of those doc tests runs include bytes or include stir with a path. What is that path relative to? Is it relative to the Rust file that included the markdown file, or is it relative to the markdown file? Well, in the 2024 edition, it is relative to the markdown file, which is where that doc test was written rather than the Rust source code. So it sort of follows the principle that we've established for almost all relative paths in both Cargo and Rust C, which is that relative paths are relative to the file in which you're finding the path. And so that now also upholds for things like doc includes.
Last up, we have Rust format changes. And so I think this is the first edition where Rust format itself defines kind of a style edition, where the idea being Rust format doesn't want to make changes, because whenever Rust format changes anything, it can cause like massive diffs to anyone's code. And so Rust format tries to avoid changing things in such a way. But if you ever want to change anything, you've got to at some point decide, hey, now's the time. And so the idea is they have their own sort of style edition mechanism where I think in the past it might have been tied directly to the edition. So when you upgraded your edition of your code, you would have gotten the new edition of a Rust format as well, right? And I believe this is now decoupled, and so you can separately say, hey, I want to use this edition style while being on the newer edition. And so there's a lot of changes in Rustdoc, Rust format, far more than we can get into here today. I think sorting was interesting. You want to talk about that?
Yeah. So one of the primary reasons I think here, or one of the sort of styles that changed in Rust or that they wanted to change in Rust format that would have caused a bunch of diffs for people, and they want to give people a way to get to the new edition without adopting the new style straight away. So they needed the style edition thing, was something they called version sorting, which is that Rust format now has a new sorting algorithm that it applies in a couple of different contexts, and one of the main ones is for imports. So previously, the Rust would generally use ASCII-betical, they call it. This is basically like the thing where you just sort by the ASCII characters and then you ignore Unicode. This is fine, but it's not really necessarily what you want to happen. For example, if you sort by ASCII-betical, then things like U8 and U16, you're going to end up with the U16 coming first and then the U8 because, well, 1 is smaller than 8 and you're comparing character by character. With this new version sort algorithm, instead what happens is they compare Unicode characters lexicographically and extract things that are numbers and sort those according to as the numbers, not as though they're digits. And so in prior editions, you would end up with things like U16 followed by U32 followed by U64 followed by U8. And in the new one, you will get U8, then U16, then U32, then U64. It also changes the order of capital letters versus lowercase letters. So in the new style edition, you end up with capital lettered words first and then lowercase letters, which is not the case for ASCII-betical. Because ASCII-betical just compares like the byte value of the ASCII characters. And so it, the
lowercase is a lower number.
Yes, exactly right. And so this allowed them to make this change, but it may cause quite a lot of churn in people's code. And so hence this need to be able to give a mechanism for people to choose not to adopt it yet.
All right. And I think that's it. Is there anything else we want to talk about today?
No, I think we are all the way through the 2024 edition. And so we can celebrate entering 2025.
It took us less than, in theory, right? It took us less than a year to cover the new edition.
I think that's pretty good.
Yeah, it's pretty good.
I think we've succeeded.
Yeah.
And so now we are ready to wait for the 27 edition. Mm-hmm. And we're just going to sit here until that happens.
All right. Well, in the meantime, folks, have a good time.
Or have a bad time. If you really have to, then have a bad time.
As long as you do what you want to do. If you want to have a bad time.
Or don't.
By all means.
If you don't want to do what you want to do, then don't.
Oh, yeah. If you want to do what you want to do, then there you go.
See you all on the other side.
Farewell.
Bye, everyone.